Catboost is a very cool looking gradient boosting implementation. It's open source from memory. It's developed by a Russian giant called Yandex, and I've certainly gotten some very good results from it in the past. I seem to be looking at NumPy 1.16.4. I kind of hope that I'm on the same version of our image that you are, and therefore you've got the same. Otherwise, this thing's not going to work for you. The only thing I did that I can think of which might have changed my version is around about a week or two ago, I installed the category encoders and that updated sklearn. I don't know why that also updated NumPy, but if this all fails horribly for you when you get there, well, you have a choice. You can post a note on Moodle, and if I have a chance I'll see what I can do, or you can just stick to XGBoost or LightGBM. I've written quite a few notes in here which you're welcome to read as to how I ended up with my final parameters. Once again, there's various parameters which you need to get familiar with if you want to use the Catboost regressor. Some of them should be very familiar. Depth is familiar. What else do we have? By default, the learning rate is defined automatically based on the dataset properties. This should be close to optimal, so that would be amazing if we didn't need to bother figuring out what the learning rate was. L2 leaf regularization should remind you a little bit, going back to our decision trees, where we had the complexity parameter, where there was a cost to each leaf. OD seems to be just the equivalent of what we've seen so far, early stopping. OD, they call it overfitting detector. It's exactly the same as early stopping. Before building each tree, it sees how many trees was it since the optimal mean absolute error, and if that is more than 100 trees previously, then it stops. There's not a lot more there to talk about, I don't think. Let's define the model and let's fit the model. It gives you this cute graph as it's fitting it, and it stops. You can see that it found the best at something like iteration 2052. Can't quite figure that out, whether that's 100 iterations since the best or not. But it's cute anyway, the pretty graph. How does train and predict work? Well, there's a result which is actually somewhat similar to last year, although not quite the same. Do that again, but this time over the whole training data. And I'm not going to plot it. There's not much point plotting it because there isn't any validation data. And finally, we get a pretty decent test error, but rubbish overfitting, as you can see. Now, I did say we would come across something called HyperOPT, and you know, it's been a whole day of recording, and I'm not quite sure that I have the energy to go into this in gory detail. I think it's something that you can look up yourselves. I would strongly recommend, if you're doing anything with Catboost, that you look up this link over here, which is really good. But in fact, even if you're training LightGBM or XGBoost, I think HyperOPT is something worth looking at. What I have done over here is I've told HyperOPT that I don't like overfitting. And I've told it over here, I've got a function which tells HyperOPT what it should try to minimize. So what it should try to minimize is my penalized MAE. And I've told it the penalized MAE is the validation MAE plus some cost, 25 cents per dollar of overtraining. If the overfitting, is more than 2,000, and then another 25 cents if the overfitting is more than 3,000. So it's going to be strongly encouraged not to overfit. Well, now that I am looking at it, just briefly what's going on. You just tell HyperOPT to minimize an objective function. It's essentially just a minimizer. What is the objective function? It's a model, first. Once we've got the model, we need some kind of way of estimating our test error. That is done with the CV function, which has been loaded from Catboost very conveniently. So you just give it all of your training data, and it estimates the test error using cross-validation. It sticks it all in CV data. We can then get the validation and train, and finally we can work on our penalized function. I'm looking here and I can see that I've got a minimum of something over here. I'm not quite sure what's going on in this, and I'm not going to look right now, but I'm hopeful that you will find it if you follow this tutorial up there. What I am going to do is run this code. I'm telling it over here that we're going to find the minimum, a little bit like you did with SciPy a little bit earlier on, those of you that find the minimum using the SciPy minimizer or maximizer. How many models is it allowed to try? Maximum of 50 models. The way it's finding this minimum is something called a tree of Parson estimators. I'm going to point you to the original paper, but I'm not going to talk more about it. The only two things I'm telling HyperOPT that it can try and change is the leaf regularization, which can be uniform between 0 and 5. So it can choose any number between 0 and 5. And, sorry, it's a log uniform, which probably means the final thing is e to the power of that. Depth can be anything between 3 and 8 by the looks of it. Here we go. Well, that took a very long time. It must have been at least an hour or two since I set that running, but it's done 50 sets of cross-validation. Let's see what the best model is. Depth 0, which means 0 above the 3 that I started it off with, and a fairly high leaf regularization of 93. If you remember, we set leaf regularization like this. It was a log uniform, so that means it could lie between e to the 0 and e to the 5. E to the 5 is about 148, and it's chosen 93. If you remember, I was playing around with regularization for leaves of around about 40, 60, something like that. So 93 is quite a lot higher than I might have guessed. Let's fit one final model with these parameters. Depth 0 plus 3, regularization. You can see when I did this last year, it was 95, and the default is 3. I've made a note that I couldn't get MAE to work as a loss function. It's not ideal, really, is it? Because we would probably have gotten a better performance if we could get it to work. And here we go. Once again, slightly less good than last year. I just wonder if I put in the actual leaf regularization that it wanted, if I'm going to get something slightly better. Where does this leave us? I've just had a look at our ElasticNet results from when I did H2O on one-hot encoded variables and the linear splines, and these results are remarkably similar, both in terms of the overfitting. I think Catboost is slightly less overfitted, and ElasticNet is slightly ahead in terms of the final performance and the test data. What does that mean? Well, the ElasticNet model is a far more interpretable model. If somebody asked you what the formula was behind the ElasticNet predictions, you could give them a simple additive model, which would give them the results. Catboost was, in some ways, much easier to fit. We literally didn't need to do anything. We just got Catboost going and stuck some, but by no means all, of the hyperparameters through HyperOPT. However, in practice, a great many data scientists say that gradient boosting is the best thing since sliced bread, and it gives the most powerful models. So why am I not managing here to get Catboost to outperform ElasticNet? Well, maybe I just didn't try hard enough, but also maybe the dataset isn't quite big enough. At 2,700 observations, it's probably going to be quite hard to outperform other sensible models, and our ElasticNet was a sensible model. Incidentally, we could probably get a little bit more about it. We could get a little bit better performance out of ElasticNet by trying to add some interactions and engineer a few features. that is it for week 5. I kind of feel that along the way it was a bit more complicated than it needed to be. All we really did at the end of the day was introduce 2 powerful machine learning models. The random forest, which just simply gets rid of noise in individual decision trees by building lots of random decision trees, hence random forest, and taking the average. That introduced us to some new vocabulary because we started that off with bagging, bootstrap, aggregating. We didn't talk about out-of-bag estimates. I recommend you look that up because it is a very useful feature of random forests. We then moved on to gradient boosting, and we realized that this was just a more flexible and more powerful application of the gradient boosting that we had seen when we started off with linear models. There's nothing more to it than that. Just have a slightly more flexible model underlying each step you take down the loss function. We saw 3 applications of gradient boosting: XGBoost, LightGBM, and Catboost. That is it now. Goodbye for week 5 and see you week 6. Bye now.